Hello friends, welcome to my channel. This is my third video on vectors. So let's get started. Now the first topic for today is multiplication of a vector by a scalar. Suppose I do an operation on vector like this. Say A is a vector with which I have multiplied a scalar quantity k. Now if I multiply this, I will land up with another vector r. Now if k is just a number, then the unit of vector r is going to be same as unit of vector a. For example, say a was a velocity vector. Say a was a velocity vector 10 meter per second due north. Okay, so when I multiply k with it, say k is any number, say 2. When I multiply k with a, I'll land up with 2 into 10, 20. Okay, so I will land up with the magnitude of r as 20 meter per second due north. So you can make out from this video that the unit of vector a and the unit of vector r is going to be the same, because your k is just a number and not any physical quantity. But there can be another example. Say this was example 1. Take another example. Example 2. Say we have a vector v, say a velocity vector, with which I multiply a quantity called mass, and you all know very well that I will get linear momentum. Okay, so this is an example in which the unit of vector v and the unit of vector p is not going to be the same. Alright, so keep this in mind next time when you multiply vector with any scalar. So the scalar is a number or it is a physical quantity, you have to be careful about it. Now let's go to next topic, unit vector. Now a unit vector is a special kind of vector whose magnitude is unity, 1, whose magnitude is 1, just 1. So what is the use of this vector? It is there only to show you the direction. So let me write it. A unit vector indicates a direction. Okay. For example, say a is a vector. If I divide vector a with its magnitude, means only the numeric value, only the magnitude excluding its direction, then I will land up with the unit vector a, and I denote it as a cap. So a cap is, this cap indicates that it is a unit vector whose magnitude is 1 but the direction is same as that of vector a. For example, it is a common practice. Say I am drawing our 3 coordinate Cartesian system. This is my x-axis, this is my y-axis, and this is my z-axis. Suppose it is a common practice to indicate a unit vector in the direction of x-axis as I cap, a unit vector in the direction of y-axis as j cap, a unit vector in the direction of z-axis as k cap. So next time if I write a vector like this, say this is my 3D coordinate system, okay, and this is my origin. So I'll write 0, 0, 0 because this is a 3D plane. Now suppose I want to indicate position of a point. Say this is some point with coordinates 2, 3, 4. Suppose if I join from origin to this point, this is going to give me the position vector of this point P. Now this position vector r can be written as 2i plus 3j plus 4k. So it is very important to mark here the usage of this unit vectors. Okay, so I cap is showing you that this position vector r has component 2 along x-axis, has component 3 along j-axis and has component 4 along k-axis. So this unit vector is giving you the direction of the vectors. Okay, let's come to the next topic, resolution of a vector. Now suppose in my 2D plane, I'm just taking example of a 2D plane to make my things simple. Say I have one vector A. Alright, now say I'm dropping perpendicular along x-axis as well as along y-axis. I'm simply dropping perpendicular. The magnitude of this perpendicular, say OP, along x-axis can be represented as AX, and the magnitude of, say, this component along y-axis is, say, OQ. I am representing as AY. I can say AX is the component of the vector A along x-axis, AY is the component of vector A along y-axis, and I can write vector A as AXI. I cap again indicates a unit vector in direction of x-axis, AXI plus AYJ. Okay, I can even find out the magnitude of this vector A. How can I find out the magnitude? I'll simply do this, square root of AX square plus AY square. I can even find out this angle. So this angle is theta. How much is this angle theta? I can make out. I can use trigonometry here, and I will say tan theta is equal to AY by AX. You can simply make out here, if this one's OQ magnitude is AY, then definitely over here this magnitude is also going to be AY. So I can use trigonometry here for triangle, say OPC. In triangle OPC, tan theta is AY by AZ. So your theta is going to be tan inverse of AY by AX. Okay, hope you have understood the concept. Now let's move to the topic of some spatial multiplication of vectors. The first spatial multiplication is called scalar product or dot product. Okay, now how this product is calculated, how it is indicated. Say I have two vectors A and B and I want to calculate this dot product. I will simply write A dot B. Okay, so this was my vector A, and say this is my vector B, and the angle in between is, say, theta. So the dot product of these two vectors is going to be A vector dot B vectors, which can be expanded as magnitude of vector A into magnitude of vector B into cos of the angle between them. So how much is the angle between them? It is theta. So it is cos theta. For simplicity we write like this, AB cos theta. Okay, we can show magnitude like this. Instead of writing this vector A and then modulus sign to show its magnitude, we can simply write A. So it indicates I am talking about only its magnitude, only its numerical value, and not about its direction. Let me cite some examples from physics for this dot product. The first very simple example which I can give you is, say, work. Okay, what is work? Work is simply the dot product of force and displacement. Now you can very well understand from this example that I am multiplying two vector quantities, okay, but I am landing up with one scalar. So this is very important result over here, that whenever I do dot product of two vector quantities, my answer is a scalar quantity, and that is the reason why dot product is also called scalar product. Okay, let us take another example. Let us differentiate this equation only. Let us do ddt, differentiate it with respect to time. Let me give you second example of scalar product in physics. For that, let us differentiate this equation with respect to time. ddt of w f dot d dt of s. Now in case you are having difficulty in understanding this concept of differentiation, please see my video on differentiation. I have given the link in the description box, as well as you can click the I button on the top. Okay, so here we see that the rate of doing work from physics concept we know is called power. So I can write here power is F dot. Now the rate of change of displacement with respect to time is nothing but velocity. So here I arrive at my second example of dot product, which is called power. Power is the dot product of force and velocity. There are some interesting properties of vector product. So let me state it one by one. Properties of scalar product. The first property is that the scalar product is commutative. Now what does it mean? It simply means that if I do A dot B, it is going to be same as doing B dot A. It has to be, you know, because this is a scalar product. Okay, this is a scalar product. The answer is going to be scalar. So whenever I do A dot B, I will get the same answer as B dot A. Alright, second property, my scalar product is distributive. It is distributive. What does it mean? It means if I do this kind of, say, calculation, A dot with B plus C, it is same as doing A dot B first and then adding it with A dot C vector. Okay, third property. Let's come to third property. Let's see what happens if we multiply two orthogonal vectors, means two perpendicular vectors. I'm writing here, okay, dot product of two perpendicular vectors. Suppose I have vector A and perpendicular to it I have another vector B, and I want to calculate its dot product. So I will do A dot B, which is mod A mod B, cos of the angle in between them. Cos is cos of 90 degree, you know it is 0. So A dot B is coming out to be 0. Now this result is very helpful, you know. Sometimes while doing numericals you will be asked to prove two vectors are perpendicular. So in that case you can do this calculation of A dot B, means you can do the calculation of scalar product or dot product of two vectors, and you can show that the result is coming out to be 0. So that will prove that two vectors are perpendicular. Similarly, we can calculate the scalar product of two parallel vectors. So I have two vectors here, A and vector B. Clearly the angle between them is 0 degree. So let us find out the scalar product. A dot B, A B cos 0, and we all know cos 0 is 1, so it is simply going to be AB, means it is simply going to be the product of its magnitude, right? Fifth property, let us see the scalar product of a vector. Scalar product of a vector with itself. Let us find out this. Okay, let's do this. A dot A, it is A cos 0. Just a minute, let me erase this. A cos 0 degree. So cos 0 is again 1, so it is nothing but A square. So scalar product of a vector with itself is simply square of its magnitude. Let's find out the scalar product of unit vectors. Scalar product of unit vectors. Say I do I dot j. I write magnitude of I 1, magnitude of j is also 1. Say multiplication 1 into 1 cos 90 degree. We all know that I and j are perpendicular to each other. if you remember this diagram which I drew just few minutes before, I cap is a unit vector along x-axis, j cap is a unit vector along y-axis, and z cap or k cap, sometimes we write as k cap also, is a unit vector along x-axis. So cos 90 is going to give you 0. So dot product of two unlike unit vectors is going to give you 0. You can test this with some other example also, like for example I do j dot k, again you will get 1 into 1 cos 90. So once again you are getting 0. So you should remember, whenever you do dot product of two unlike unit vectors, you get 0. Okay, now what if I do with like vector? If I do say I dot a, I'll get 1 into 1 cos 0, which is nothing but equal to 1. Similarly, if I do j dot j, I will also get 1. If I do k dot k, then also I will get 1. Okay, now the scalar product of two vectors given in component form. Okay, so what if two vectors are given in component form and you have been asked to calculate its scalar product? Suppose I have a vector a which is like this, axi plus ayj plus azk, and say you have another vector say b which is say bxi plus byj and bzk, and you have to calculate say a dot b. Now the scalar product calculation is very easy. You simply multiply the components. You check what is the component of, means what is the component along x-axis of these two vectors, and then you simply multiply. So component along x-axis is ax and bx, so simply product of this. Then we do this plus into plus plus ay by, this is simply product of the j component. Then again plus into plus is plus, product of the z component. Let me illustrate this with an example. Say vector a is 2y minus 3j plus 4k, and b vector is say 2i. Let's take another number here, not 2, let me take some other number, say 3i plus 4j plus 6k. Okay, and I am asking you to do its dot product. So see, 2 into 3 6, minus plus minus, 3 into 4 12, again plus into plus is plus, 4 into 6 is 24. So you can do this calculation, 30 minus 12, and then you can write the result. Okay, yes, 18. So this is my answer. Alright, I hope you have understood. Stay tuned to my channel, and in my next video I will discuss about vector product और क्रॉस. डियर स्टूडेंट्स, अगर आपको मेरा वीडियो अच्छा लगता है तो प्लीज़ लाइक, शेयर एंड सब्सक्राइब माय चैनल. अगर आपके पास कोई डाउट है या फिर कोई सजेशंस है तो यू कैन कॉन्टैक्ट मी एट amiclasses@gmail.com.